This problem is number 14 on page 240. Y double prime minus 2y prime plus y equals to e to the x natural log of x. If you have the book I'm using, you'll see that on the right hand side they wrote LOGX. Remember, this book was written in 1963, and I think the standards have changed a little bit, perhaps, because these days we interpret LOGX as base 10, common log x. And but what he really meant was natural log x. I'm pretty sure of that. And so it's his habit in the book to write natural log as LOG. And I've seen that in complex analysis books. That's kind of common way to write the logarithm, the natural logarithm. But he really did intend e to the x ln x. Alright, so our first order of business is to find the complementary solution. The characteristic equation is m squared minus 2m plus 1 equals to 0. And this is a perfect square. M squared, m minus 1 squared equals to 0. So we get a double root, 1 and 1. So that means our complementary solution is going to be c1 e to the x plus c2 x e to the x. There we go. So with the double root, we have to repeat the e to the 1x by multiplying one of those by x. Alright, so let's write out our particular solution then. It's going to be u1 e to the x plus u2 x e to the x. And now our job is to solve for u1 and u2. Okay, so where do we go here? We need to note that y1 is equal to e to the x, and y1 prime will be e to the x, y2 will be x e to the x, and y2 prime will be that derivative. Well, this derivative is going to be 1 times e to the x plus x times e to the x. So I'm going to write this as e to the x times x plus 1. There we go. So we have all those in place. The y's and their associated derivatives. Okay, so I still don't have this memorized. I'm not sure I want to memorize this, but the variation of parameters formula, u1 prime would be 0, y2. So I'm just going to write them in this time. So y2 is x e to the x, and then we have q of x divided by a2. Well, a2 is equal to 1, so it's q of x e to the x natural log x, and then y2 prime, which is e to the x x plus 1. Alright, and then this is divided by, let's see, y1, y2 across the top, so that's e to the x, and x e to the x divided by the derivatives, e to the x and e to the x times x plus 1. There we go. Alright, it's a mess, isn't it? Okay. So, and kind of like my remark in last video, we could just put 0 there, because in a 2 by 2 determinant, if you have a 0 in this corner, then this product is going to be 0. It doesn't matter what goes there. So I have 0 minus this product. And what is this product? It's going to be minus x. Then what's e to the x times e to the x? That's e to the 2x, isn't it? We add exponents. E to the 2x times natural log of x. Divided by, this product will be e to the x times e to the x. That's e to the 2x times parentheses x plus 1. Minus this product, going backwards, this product is x times e to the 2x, x e to the 2x. So if you look inside here, we have e to the 2x, and this term, that term, and that term. So we can divide those off. That's pretty nice, isn't it? And we have x minus x. These x's will cancel. And so after I divide off the e to the 2x, my denominator is 1. So u1 prime is going to be minus x natural log of x. There we go. So we still have to do an integral here. We have to integrate that in order to get u1. So let me do a little erasing here. So we have u1 prime equals to minus x natural log of x, which makes u1 equal to the integral of negative x natural log of x dx. How do we do that? Well, to me that looks like it's probably integration by parts. Let's let u equal to natural log of x, or u be equal to x. Let me try u equal to, now this u is different from these u's over here. This is straight integration by parts. So let's let u equal to natural log of x, and dv equal to x dx. So I have u dv, and then du is going to be 1 over x dx. V, integrate x dx, we get x squared over 2. So I have minus u times v, that's, so this negative, u times v would be x squared natural log of x over 2 minus the integral of v du, and v times du is going to be x over 2 dx, because, well, the x is canceled. And so u1 will be minus x squared over 2 natural log of x, and then the negatives cancel, so I have a plus here, and when I integrate this I'll get x squared over 4. So plus x squared over 4. There we go. Alright, so I'm going to record that somewhere, and then we'll go after u2. Well, I had a few phone calls interrupt me, and I kind of lost my place, but here is u1. I think we derived that earlier. And I've written out u2 prime using Kramer's rule again. And so, just a matter of picking off all the right functions here. All right, so let's see what we got here. So this determinant, I multiply here, I'll get e to the 2x, natural log of x, minus 0. So this diagonal, and then minus that diagonal, of course that's 0. And down below, we did this a minute ago, let me see, it's going to be e to the 2x times x plus 1, and then minus x e to the 2x. So a little bit like before, we can cancel off the e to the 2x's by division, and that will give us natural log of x, because this x will cancel that x. So u2 prime is equal to natural log of x. Alright, so once we integrate that, I think we're in business. So let me rewrite this and make some room. Now we have u2 prime equals natural log of x. So u2 will be the integral of natural log of x dx. And you can look that up in a calculus book probably and find it. I'm going to solve it. It's a classic integration by parts problem. And we solve it by letting u equal to natural log of x, dv equals to dx, and then du would be 1 over x dx, and v would be x. So when I plug all that stuff in, I have u times v, x, natural log of x, minus integral of v du. So when I multiply these together, v du is just going to be, the x's cancel, I'll have dx. So this results in x, natural log of x minus x, or if we factor x out, we'll have natural log of x minus 1. So I'm going to write that up here, and then we'll work out the general solution. Here is U2. I wrote it over here. Now we can begin to write out the general solution. Before I do that, I'm going to combine these together. I'm sorry, I'm going to factor out the x squared part. And let me see, if I make this 2 over 4, then we could factor out u1 would be, let me see, I can factor out x squared over 4, and that will leave us 1 minus, what, 2x, 2 natural log of x. 1 minus 2 natural log of x. Okay, so I hope that's right. I think it is. Yeah, appears to be. Alright, now we can write out the general solution, which is, first of all, the complementary solution, c1 e to the x plus c2 x e to the x. And then we have y in particular will be u1, which is this stuff, times e to the x. So plus e to the x, x squared over 4, parentheses 1 minus 2 natural log of x. And then plus u2 times x e to the x. So that's plus x e to the x times this would be x squared e to the x times parentheses natural log of x minus 1. Alright, so it looks like we could factor out e to the x here. E to the x and nothing else factors. So it gives us c1 plus c2x plus x squared over 4, parentheses 1 minus 2 natural log of x, plus x squared times parentheses natural log of x minus 1. And boy, is there anything else we can do? Yes, we can, can't we? Because we can do a little bit of combining here, can't we? Alright, so this problem just never ends, does it? If I take out x squared, I'll end up with 1/4 minus natural log of x over 2 plus natural log of x minus 1. So we can combine a couple of numbers together there. I'm just going to throw caution to the wind, erase all this, and try to write out a final a general solution here. So y would be e to the x, parentheses, c1 plus c2x plus, alright, I have got 1/4 minus 1 is minus 3/4, so it's minus, we make that minus 3/4 x squared. Okay, try to make that a little clearer here. And then we have x squared times natural log of x minus 1/2 of natural log of x, so that's plus x squared natural log of x over 2. So, there we go. Now for the moment of truth, I'll check the book, which seems to be invariably right on these problems. Okay, so number 14. They organized it a little differently. They took this part, have e to the x c1 plus c2x, so they have this as one set of parentheses. And then over here they've taken out, and I think I messed up here, didn't I? That should be an x squared, not an x up there. There we go, x squared. Right? Yes, because we had x squared. So they also put a second parentheses in, factored out x squared e to the x, and what's remaining is 1/2 natural log of x minus 3/4. So we got it. Anyway, so there's a variation of parameters, method of variation of parameters. I thought I would mention, if you do have this book, page 240 has some other problems here, 16 through 20, where there are non-constant coefficients. And it says, use the method of variation of parameters to find the general solution of each of the following equations. Solutions for the related homogeneous equation are shown alongside each equation. All right, so for example, let me write one of those up here, because a couple of loose ends I want to tie up before we leave this topic of variation of parameters. This is problem 16 on that same page. X squared y double prime minus x y prime plus y equal to x, semicolon. And then they gave you the basically the complementary solution. Y complementary would be c1x plus c2x natural log of x. In other words, if we plug either of these into here, we should get 0. And so here's a second order linear differential equation with non-constant coefficients. It is possible to solve this by variation of parameters, and but the trick is you would have to know what the complementary solution is, and I don't know if that's terribly easy to get or not. I suspect the author may have just started here and come up with this differential equation. I don't know. So that's one of three little issues here I want to tie up loose ends on. It's possible to use this on other problems that do not have constant coefficients. What's required is to have knowledge of what the complementary solution is, and that's another issue right there. But the book gives you a few problems like this where this information is known, given to you. All right, that was one issue I wanted to tie up. Another one is, how good is this method of variation of parameters? Well, it's only as good as if you could integrate u1 prime and integrate u2 prime. So, as you often see in calculus, it doesn't take much to create something for which we can't integrate and get a closed function. But one could use some type of approximation technique, I suppose, if you got a function you couldn't integrate. But and it would be easy to stumble into a problem where that's the case. So there's kind of weakness in this method. It sort of works all the time, but then it doesn't, because you may be faced with something that's not integrable. My third point is that you can adapt this method to higher order equations. You could do if you did a third degree equation, you could work it out and end up with 3×3 determinants. I've never attempted that, and primarily because I don't run into third degree or higher differential equations when it concerns applications to our real world. Not saying those aren't out there, I'm not familiar with them. Anyway, that's my presentation on variation of parameters.